So a few weeks ago, I reposted a roast video that I did with a technician that found a grounded compressor, I think he said, because he said that compressor windings shrink and grow as they heat up and contract. But he had put gauges on the unit, and the unit was obviously dead. I made the comment, so your opening move, you find a grounded compressor, is to put gauges on it. And literally like hundreds of comments, especially on the dumpster fire that is Facebook, was saying, well, how else would you know if it was flat? You wouldn't want to quote a compressor if there was also a leak. Yeah, I know. You don't have to actually put gauges on the unit to determine whether it's flat or not. I can take the key to my shed and push the Schrader in and see whether there's gas in it or not. Here's the thing. I think as technicians, and I used to be one of them, to put gauges on the unit is your idea of being like thorough. And that's commendable. You want to put gauges on it, you want to check the performance of the unit, but putting gauges on the unit is not how you do it. And it was a very long time before I realized that. And I was the gauge up technician for much longer than I've been the non-invasive technician now. What do I mean by non-invasive? Well, that was something that I learned by following Jim Bergman and Measure Quick. And if you understand enough about the refrigeration cycle, then you don't need to actually know what the refrigerant pressures are in order to check the performance of the system. Put gauges on it. I wanted to check superheat and subcooling to make sure that that commercial unit was running good. I didn't want any callbacks. And because of that, I rarely got callbacks. And then when I started my own business and I started training technicians of my own, we checked superheat and subcooling on every call. Unless you were just out there the day before and you're back out there because your dumb butt left the disconnect off, you're checking superheat and subcooling on every call because I didn't want callbacks. I didn't want units that were just a little bit low on gas to end up biting us just a few weeks later, and then I end up eating the call. So I get it, but our industry needs to get away from that being the metric of checking performance, because it's not a very good metric at all. You should not be gauging up on every call, and you should not definitely be treating your gauges like some kind of security blanket that you don't feel like that you know anything about the unit unless you put gauges on it. So you walk up to a dead unit, trip circuit breaker, unit's not running, and instead of like getting your meter out, you put gauges on it first. Like, that is dumb. So let's talk about some scenarios where maybe we might be inclined to put gauges on it, but we don't actually have to gauge up. All right, let's take the scenario I just mentioned. You walk up to a unit, outdoor unit's not running, compressor's not running. Why would you put gauges on it? Well, you're like, well, to make sure that I have refrigerant in the system, make sure it's not flat. Well, that's the only thing that's going to tell you. It certainly isn't going to tell you if the unit's a couple of pounds low. All it does is tell you whether the unit has just enough refrigerant in it to be able to hold that standing pressure. But it doesn't tell you whether it's 2 or 3 or 4 pounds low. No, you would need the system to be running in order to determine that. So does it really give you a lot of information to begin with? Not really. And what's the risk? Why would you not want to gauge up? Well, if I've got a unit that's dead, especially if it's a grounded compressor, it might be a burnout. And now I'm connecting my hoses to a unit that's contaminated with acid. And then every system that I work on after that could be contaminated with acid again. So I've actually done more harm than good for that little bit of information that it told me that the system has barely enough refrigerant in it to hold its standing pressure. I've risked contamination. That to me is not worth it. I would much rather take like one of those little quick tests, those acid tests, and just push in the Schrader. And first of all, I can see if it's got any refrigerant in it at all. If I push in, especially on the liquid line, then I'm going to see whether it's got liquid in it. So I know if it has at least enough standing pressure in there to have a liquid. And I'm also going to know whether the system has acid. That to me is a much better test than just hooking up your gauges. What's another scenario? You're on preventative maintenance, not even a service call. You're just checking performance. Why would you need to gauge up for that? Do you need gauges to tell you that the system has a good temperature split across the evaporator? Do you need gauges to tell you that the system doesn't have enough airflow? Well, some people may say yes. I know that you don't need pressures to know whether the system is low in refrigerant, not performing correctly, or has an airflow problem. First thing that I do when I'm on a call every time, and you guys know this when I've talked about my 60-point assessment, is that I'm going to do a visual inspection on the air filter. Very first thing that I do before I look at anything else, hands in pockets, look at the air filter. I'm also going to take the panel off the indoor unit. I'm going to look at the indoor coil, the blower wheel. I'm going to look at ductwork to see if anything is obviously undersized, dirty, could be restricting airflow. The other thing that I'm going to do is take a static pressure test. Now, let's say that everything is clean. I'm going to check my static pressure. Now, as I continue to work on units repeatedly, like if you have a service agreement on a unit, you can check the static pressure, and then you can write that static pressure down next to your test port. In fact, TEC makes a cool little tag that is either adhesive or it sticks to the side of the unit where your test port is, and then you can write down what that static pressure is. And so that I know that if I've checked this unit before and I've done a commissioning on it, or I've been through it and I've checked the static pressure and matched it up with the airflow chart, that the next time that I come out there and it's reading the same static pressure, I know that my airflow is still good. Now I've completely ruled out airflow across the coil being a performance problem. And then the only thing you need to know at that point is your suction line temperature, your liquid line temperature, and then your return and supply temperature and humidity. You can plot that into MeasureQuick using their non-invasive tests, and that'll tell you everything that you need to know, and you don't need to gauge up. Think about it. Do you gauge up on your refrigerator every year to make sure that hasn't leaked any refrigerant out? Of course not. Do you do that to a water fountain or a water cooler in a commercial building? Of course not. You know that there's a problem when you start seeing a performance change. Your food isn't getting cold, or the water coming out of the water fountain isn't getting cold. Then you know. Well, obviously we don't want to wait that long on a heating and air conditioning unit, but when we're out there twice a year, we can be doing non-invasive checks, and there is a lot that we can tell with just those 4 probes. We check our liquid line temperature, suction line temperature, return temperature, humidity, supply temperature, humidity. But on a normal maintenance, there is no need to gauge up unless one of those probes is giving you a temperature that's out of range. What is in range? Well, you can probably develop what your range should be. Obviously, you know that you need a good 20-degree split across the evaporator, but you can also just plug it into MeasureQuick, and MeasureQuick gives you those little gauges with blue if it's low, green if it's good, red if it's high. And what I used to tell my technicians, once we got away from gauging up on every call, I would tell them to do non-invasive tests, and if anything was in the blue or the red, then go ahead and gauge up. But if everything looked okay, and it was all within the proper range, there was no reason to connect your gauges. Now, when I connect my gauges, I'm actually, when I actually have to gauge up, it's connecting a pressure probe to the suction and the liquid line, or low side and the high side. I'm not actually using a manifold and hoses. In fact, the only time that I connect my manifolds and hoses are when I'm recovering refrigerant. And that leads me to another comment that was in that post that I made. Well, if you don't ever gauge up, how do you recover refrigerant? If you're so worried about the unit being contaminated, what do you think is going to happen when you recover that refrigerant out of the unit? I have an old crappy set of gauges that I use when I'm recovering refrigerant, because I don't know what's in there, especially when we were going through the R22 to R410A phase out, and now we're in the 410A to A2L transition. You're going to be removing various types of refrigerants. It's really not practical to have a good set of gauges for every single refrigerant you're going to work on, especially if you do things like refrigeration, where you may be working on 8, 12 different kinds of refrigerant. So I have an old crappy set of recovery gauges. Like the suction line needle is like broken off. It's like laying off in the bottom of the gauge because I've got a pressure port or pressure gauge on my recovery machine. And this is just this old beater set of gauges. And all they're there to do is to move refrigerant. In fact, when I'm adding refrigerant to a system, I still don't use manifolds. I do have a good set of manifolds as a backup to my smart probes, but I've got a T-fitting and a hose, and I just connect that to my refrigerant, put the refrigerant on a scale. The hose has got a valve to it. That's how I typically add refrigerant to a system that I'm working on when I'm adding, virgin refrigerant in. So again, there's like no need to carry around a set of manifolds. They're big, they're bulky. If you're working on one system after the next, there's more of a chance of getting contaminated with acid, with other contaminants, with moisture. Use pressure probes. But even then, you still don't have to check pressures on every call if you understand the refrigeration cycle. So when I hear people talk about gauging up on every call, these are people that don't understand the refrigeration cycle as well as they think they do. If you understand things like approach temperature and design temperature difference, you don't really need to know what your pressures are. Let me give you an example. Design temperature difference is the difference between your return air dry bulb and your vapor saturation temperature, your low side gauge temperature. Well, you may say, well, wait a minute, how would you know what that gauge temperature is unless you actually gauge up? That's true. But what if we knew that just about any system that we work on should be running around a 10-degree superheat, right? So then I could take my suction line temperature and I could subtract 10 degrees from it, and then take that temperature and subtract that from my return air dry bulb, and that's sort of like my inferred design temperature difference. That should be anywhere between 30 and 40 degrees, depending on if you have an oversized coil, the efficiency of the system, that sort of thing. So let me give you an example. Let's say we've got 75-degree return air coming in. That's our typical design temperature, right? And we have a 55-degree suction line. Assuming that our system is running a 10-degree superheat, when we have a 55-degree suction line, what would be our vapor saturation? It would be 45 degrees. So then I subtract 75 minus 45, and I'm right there in that 30 to 40 degree range, right there on the low end of it. So really, if I saw that, I would not need to gauge up. And that is the secret sauce behind MeasureQuick's non-invasive system testing. That's how they're able to tell you what your temperature should be within a range without actually knowing what the pressures are. So I'm not telling you to be less thorough. I'm just telling you to try interpreting the information that you already have without actually opening up the system, risking losing refrigerant, possibly contaminating your tools, and you already have that information. You just got to think about it a little bit. Here recently, in the last few years, I've been more interested in what my delivered capacity and my delivered efficiency is than I am like worrying about making sure superheat and subcooling is dialed in. I'm putting on my return to supply cyclometers. I'm checking my airflow. Obviously, if you're just using static pressure, that's an estimate. Using something like the True Flow Grid, a lot more accurate. And if you know what your return to supply psychrometrics are, you know what your airflow is, you can determine what your total BTUs delivered as well as your sensible and latent if you're in cooling mode. Then I grab my Testo power quality meter, and I'm going to measure. Let's go, dude. People have no idea that the light turns green. All right, where was I at? Oh yeah, the Testo power quality meter. That is going to be able to tell me what my true wattage is that the unit is pulling. Now you couple that with your total delivered capacity, and you know what your coefficient of performance is, or in cooling or heating mode, to know whether my heat pump is operating in any kind of efficient manner, because I'm calculating my coefficient of performance. Anything that's kind of below 3, you start getting into poor performing systems. If it's super cold outside, you may see below 3 on a heat pump, but usually a good performing system is going to be somewhere between 3 and 4 COP. So I don't need to know what my superheat subcooling is. It is not in the equation. I need to know what my return and supply psychrometrics are and my airflow. And if I'm looking for efficiency, obviously I need to know what my true wattage is. And to me, I find myself looking at those numbers because that's where the rubber meets the road. That's what's delivered to the house. I find myself looking at that a lot more closely than I am trying to dial in whether the system's supposed to have 9 degrees subcoolant, 12 degrees subcoolant. Like that, to me, it doesn't really move the needle. If your superheat changes by 1 degree, if you get your superheat down from 11 degrees to 10 degrees, doesn't really change your delivered capacity that much. It does a little bit, but not that much. So if you really want to know how the system is performing, then those are the checks that you want to do. Delivered capacity, delivered performance, efficiency, COP, SEER. You can do all those things in MeasureQuick, but simply just getting your old analog set of gauges, which you have no idea whether they're accurate or not, and getting some temperature clamps and just checking superheat and subcooling on every unit without even making sure the unit has proper airflow, that is not giving you the information you think it is. When I check a heat pump in heating mode, again, I hardly ever gauge up unless the non-invasive tests that I do first fail, where the things are out of range. And at that point, yes, you absolutely must gauge up to be able to verify that maybe the system is low on gas versus maybe have a restriction. But usually you don't need to gauge up even on checking a heat pump in heating mode. I just made a video about this a few days ago using MeasureQuick. The first thing that I'm going to do in checking a heat pump after I let it run for 10 minutes and settle out and get up to temperature is checking the temperature rise across the indoor coil. That should be anywhere between 17 and 30 degrees. 17 if it's like single digits outside, and 30 if it's like 50 degrees outside. So you can kind of create your own little scale, or how cold is it outside at this moment? Well, let's say you're checking it, it's 25 degrees outside. Well, my temperature rise should be somewhere in like the low 20s. But let's say that I'm checking the system performance out and it's a 25 degree day, and I check my temperature rise and it's 22 degree rise. I think that's pretty good. That passes test number 1. If I really want to get a little bit more thorough, the next thing that I do is check my approach temperature. That is the difference between my return air temperature coming into the indoor coil and my liquid line refrigerant temperature coming out of that indoor coil. Whenever a heat pump is sending hot refrigerant into the indoor coil, there should always be a little bit of heat left over as that refrigerant leaves the coil. If not, then that means that that coil has used up all the heat that the heat pump could provide, and that very rarely should be the case. Your approach temperature tells you how much heat you have left over in the refrigerant after it goes through the indoor coil. After it's done giving off its heat to the return air, it should still have a little bit of heat left over, and if it does not, then you've got a problem. Now with approach temperature, you can have a really high approach, which means that your liquid line is really warm compared to your return air coming in. That might indicate an indoor airflow problem because you're not giving up enough heat to the indoor coil because there's not enough air going across that indoor coil. If you have a really low approach, so somewhere like less than 5-degree difference between liquid line and return air, then you may either be undercharged or overcharged. In both cases, you can have a really low approach. In that case, obviously you need to gauge up and you need to figure out what the problem actually is. But if my temperature rise and my approach temperature both look good, I'm typically moving on to the next unit. I am not going any further. But let's say that I really did want to go a little bit further and I wanted to know what was going on the low side of that system. Then yeah, I would pull the top and I would put a clamp on the true suction line of the compressor, or maybe if you're working on a train unit, it's right there on the side panel. One way or the other, I'm going to get my suction line temperature. And now I've got all 4 probes that I need for a non-invasive system test for MeasureQuick. If I don't have my suction line temperature, MeasureQuick really doesn't know a lot about what to do. There's some missing information, but you can still use their non-invasive system testing. It's just going to throw some flags at you because it's asking you to connect that suction line probe. But again, if I fail any of those tests, then absolutely I'm going to gauge up because I have to get more information. But if those tests pass, there is no reason for me to gauge up. Gauging up is just going to tell me what I already know. So I know this may be kind of a foreign concept to a lot of you, and hopefully some of you are open-minded enough to learn more about it. And I encourage you to look up non-invasive system testing with MeasureQuick's website, with their social media posts, with HVAC School. They've had Jim Bergman on there a number of times on podcasts and tech tips talking about non-invasive system testing. I've got a bunch of videos and content out there about it. DM me, ask me more questions about how you can use that in your day-to-day process. There is no reason for in 2025 for us to be gauging up on every unit that we work on, PMs, service calls, that sort of thing. We should be able to use more non-invasive system testing, but it requires a better knowledge and a higher level of understanding of the refrigeration cycle. And actually, we're supposed to have that anyway. That's part of our job. So let me know in the comments what you think about gauging up on every job. Do you do it? Why do you think it's necessary? Have you tried more non-invasive techniques? Thanks for watching. Like and subscribe, or don't. And work safe. See you next time.